In each of the following situations, you'll be given a worded problem involving either an arithmetic or geometric progression. Pause the slide and write down an equation in the simplest form using A, D or R. So first of all, we have that the 10th term of an arithmetic progression is equal to 22. Pause the slide and write down an equation that would model this. So because we know that the nth term of an arithmetic progression is a plus n minus 1d, we know the 10th term will be a plus 9d. So we have that a plus 9d equals 22. Next, write down an equation that represents the information the 5th term of a geometric sequence is equal to 16. So we know that the formula for the nth term of a geometric sequence is ar to the n minus 1. So the 5th term would be ar to the 4. This is equal to 16 in this question. Next, we are told that the sum of the first 7 terms of a geometric sequence is equal to 24. Write this down as an equation. So using the sum formula from the formula book for a geometric sequence, the sum is a bracket 1 minus r to the n over 1 minus r. We're going to use 7 for n. We get 24 equals a bracket 1 minus r to the 7 over 1 minus r. So next we have that the sum of the first 10 terms of an arithmetic progression is equal to 82. So for this we're going to use the formula for the sum of the first n terms, which is a half n 2a plus n minus 1d. We're going to use n as 10 here. So a half of 10 is 5, 2a plus n minus 1 is 9, 9d. So this equals 82. We can then simplify this down to give us 10a plus 45d equals 82. Next we have the 7th term of an arithmetic progression is equal to 3 times the first term. So we know that the 7th term will be a plus 6d, and this is equal to 3 times the first term, which is 3a. So a plus 6d equals 3a. We can then simplify this to a equals 3d. Next, the 5th term of an arithmetic progression is equal to twice the 2nd term. So we know the 5th term will be a plus 4d, and we know that the 2nd term is a plus d. So if the 5th term is equal to twice the 2nd term, we have a plus 4d equals 2 times a plus d, which simplifies down to give us a equals 2d. Next, the sum of the first 6 terms of an arithmetic progression is equal to 5 times the 3rd term. Again, we're going to need to use the formula here. So the sum of the first n terms is a half n 2a plus n minus 1d. So we're going to substitute 6 in for n here and then put it equal to 5 times the 3rd term. So we have half of 6 is 3. 2a plus 6 minus 1 is 5, 5d. 5 times the 3rd term. Well, 5 times the 3rd term is a plus 2d. So we have this equation here. This can then be multiplied out and simplified to give us a simpler version, a equals minus 5d. Next, the 4th term of a geometric progression is equal to 8 times the 1st term. Again, write down an equation that models this. So we know the 4th term will be ar to the 3, and 8 times the 1st term is 8a. We can simplify this down, assuming that a is non-zero, which I think is a reasonable assumption, because if a was 0, then all of the terms in this sequence would be 0. We can cancel out the a's, leading us to r cubed equals 8, and if r cubed equals 8, then r must be 2. Next, the limit of the geometric progression, in other words the sum to infinity, is equal to 4 times the second term. Remember that the sum to infinity is only valid for r values between -1 and 1. So we know the formula for sum to infinity is a over 1 minus r, and this equals 4 times the second term, which is 4 times ar. We can simplify this. We can multiply both sides by 1 minus r. We can also divide by a, assuming that a is non-zero. And doing so, multiplying this all out, gives us a quadratic in terms of r. We can go further to solve this, giving us a value of r equals a half. Remember that we already know that this geometric progression must have an r value between -1 and 1, because otherwise the sum to infinity formula would not be valid. So if we had solved this and found an r value outside of the range 1 to -1, we would have known to reject that value of r. Now complete exercise 5.1 on page 300.